This is my presentation for machine learning fundamentals. So the problem that we were tasked with here was figuring out what using vacuum, pressure, relative humidity, and ambient pressure was going to be a good predictor for power output. So in the CSV that they gave us, what I did is I started by inputting the data into Databricks, and from here I created histograms so I could see the distribution of the data for each variable or each feature. So as we can see, temperature is pretty evenly or normally distributed. So is ambient pressure. Relative humidity has a slight skew to the right, and vacuum has a skew to the left. So just things to keep in mind as we're starting to do the analysis. Since we're trying to figure out relative to power output, what would be the best feature, I wanted to see when we did an analysis of a scatter plot, comparing power output to the different features, what was going to be our data results. So as we can see with the power output versus temperature, we have a negatively correlated, or rather not correlated, we have a negatively slanted, fairly, actually, I would say tightly aligned scatter plot. And as we start to look at power output and ambient pressure, scatter plot definitely loosens up, and relative humidity is kind of all over the map. So we know we're likely not going to see a high correlation on those. So using Databricks AutoML, I inputted the CSV, and from here decided to let the ML pick which model was going to be best, obviously using regression. So here, the Databricks AutoML selected the Light GBM, which is a gradient boosting machine learning model, specifically around, it's a histogram decision tree instead of essentially trying to split on specific features, or rather the sorted values of features. It actually forms leaves to then do its selection. This is actually a pretty efficient model, and this ran very quickly for me, which was pretty awesome. All right, now to the important thing. So the model was actually extraordinarily accurate and precise, and we can see here not only with the model results, but also the feature importance that we're going to be able to not only explain why the model is doing what it's doing, but also the accuracy and precision. So I am selecting the RMSE, which is going to be the root mean square error, because that essentially is the precision of the prediction. So on my training set, it was 3.13. And then on my validation set, it did actually widen up a bit, which is to be as expected. However, it did not widen up significantly, which is really good. So comparing those two, we can see that it was not a whole ton of change, which is what we're hoping for. Also, relative to the PE statistics, that root means square error. When we take a look at just how the data is distributed and the values, the standard deviation actually for this thing, I'm going to go ahead and zoom in here. As you can see, it's 17.066. So given that our essentially error of a prediction is only 3.13 on our test, and then our 3.52 for our validation, that is great in when we take that in comparison to the standard deviation of 17.066. Now, on to the feature importance. We can see here, ranked highest to lowest, that temperature is going to be the most important feature. Vacuum will be second, and then pressure, and then relative humidity is fairly not that important, which we actually saw with the correlation result with the scatter plot previously. And this is my video, so thank you for watching.